All right, new twist on this one. So here we're going to find the volume again. We're back to rotating about the x-axis, but now we're bounded by two functions on the interval from 1 to 3. We're bounded by f of x equals x, and g of x equals the square root of x from x equals 1 to 3. So we've already done this square root of x bit before, but now we've got this other function x, and we need to be bounded between those two functions and rotating around the x-axis from x equals 1 to 3. So I have that graph for you guys here. In the red is the graph of just f of x equals x on 1 to 3. And in the blue, we have the square root of x from 1 to 3. All right? So what's it going to look like when we take that region bounded in there and we rotate it around the x-axis? Well, let's take a look. There we go. So what we want to do is we want to find the volume in here, not in there. Okay, so this is actually hollowed out. It's this shape like this right there, which has a hollow inside. Okay, it's bounded by kind of this truncated cone on the outside and this like truncated bullet shape on the inside. We want to find that volume. All right, so how do we do this? Really, there's two different approaches that we can make. Let's just do a quick sketch here. Let's go 1 to 3. Set up our line like this. That's y equals x. We'll set up our curve and like that. That's y equals the square root of x. So two options. First option, could we find the volume by taking the area underneath y equals x all the way to the x-axis, rotate that, okay, so like find the volume of the outside, and then subtract the volume of the inside, the hollowed out part. And I think that's kind of the natural thing for students to want to do, and that's totally fine. You probably use techniques like this in geometry, where you wanted to find this volume of this composite solid, you took the volume of the entire thing, and then you subtracted away the parts that you don't want to include in the volume. So let's do that first. So let's do we'll call it the outer volume. Okay, that is going to be, I'll call it V sub O for outer, the integral from 1 to 3 of pi. What's my y value? My y value is x, pi x squared dx. So that's going to be pi times, I'm going to do two steps in one here. I'm going to take the antiderivative, which is 1/3 x cubed from 1 to 3. This is going to be pi times 3 cubed is 27. 1/3 of that is 9. 9 minus 1/3. 9 is what? 27/3, right? So subtract, that's 26 pi over 3 is the volume of the outside. It's the outer volume. Now let's find the inner volume, but now the radius of our cylinder, so here's my rectangle, the radius of my cylinder is now the square root of x. Whoops, wrong button. So now my inner volume, called V sub I, is going to be the integral from 1 to 3 of pi times the square root of x squared dx. So pi, radius, square root of x squared dx. So let's take our pi out. This is 1 to 3 of x dx. Antiderivative 1/2 x squared. Let's see, 3 squared is 9, so we have 9/2 minus 1/2, okay, which actually ends up being a 4 pi. So our total volume is going to be the volume of the outside minus the volume of the inside, which is 26 pi over 3 minus 4 pi. See, 4 pi would be 12 pi over 3, so that gives us 14 pi over 3. All right, so that's kind of the first way to visualize it, right? Volume of the outside minus the volume of the inside. Well, I think another fun way to picture it is to picture kind of a washer shape instead, where we take a rectangle here in this region and we rotate that around the x-axis. And when we do that, we get something, oh dear, kind of like this, right? So it's kind of like this rectangle is sitting right here, and it's rotating around, and we get something that we kind of refer to as a washer. Okay? And to find the volume that way, what we do is we say, well, it's 1 to 3 of pi times x squared minus pi times the square root of x squared dx. Okay? And we will just work through it there that way, and we can factor out a pi and say it's from 1 to 3 of x squared minus x, dx, like that. And we're going to get the same thing. And it shouldn't be difficult for us to see that, because remember, when we took the total volume in our first method, we took the volume of the outer minus the volume of the inner. And the volume of the outer was pi times the integral from 1 to 3 of x squared dx, minus the inner was pi times the integral from 1 to 3 of x dx. And we can see that those two are equivalent, right? Thinking about our properties of integrals, is that when we have a difference, we can just split it into the difference of the two, and we just distribute the pi to each. So we end up seeing the same thing. All right, let's get to another interesting example. Now let's take the volume of the solid obtained by rotating that same region. So we still have x, we still have the square root of x. We're going from 1 to 3, but now we're not going to rotate about an axis. We're going to rotate about the line y equals 4. So let's come back to this, and let's graph, well, it's probably not going to show it very well. I might jump into Desmos for this quick. So we have x graph from 1 to 3. We have the square root of x graphed from 1 to 3. There they are. But now we're going to rotate around the line y equals 4. Okay. So can you picture what's going to happen here? We have that shape, okay, and it's rotating around the line y equals 4. Let's see if we can't, in GeoGebra, still try this. Okay. So let me add in the line f of x equals, well, let's see here. I'm trying to remember on GeoGebra how we do this. Because our surface has to be a line. So what I'm going to do is I'm going to have to create a couple points and draw a line here. So let's take the point 0, 0, 4. Oops, sorry, that's on the z-axis. 0, 4, 0. There we go. That's on the line y equals 4. And let's just do another point. Let's just do 1, 4, 0. And now let's see if I can't draw a line through those. There we go. Let's see, what was that line named? Looks like it's the line I. So now what I'm going to do is I'm going to come up here and I'm going to change the line that we're rotating, and let's see if I just put an I in if it Let's try this one too. All right, big moment of truth. Here we go. Oh yeah, there it goes. There it goes. Here we go. All right, we don't get to see all of it because it gets off the graph. And I think if we zoom out, we can see it. Yes. Okay, we get that shape. So kind of take a look at what this looks like. I don't know if it reminds you of anything. To me, it might remind me of like a dog dish. I don't think we can really tip it up that way, but a bowl of some sort. So we're finding the region. It's still hollowed out on the inside, but we now have that region in between. So how do we do this? That's the question, right? How do we rotate them out the line y equals 4? So we're going to have to sketch our graph. Let me put the line y equals 4 on here. Let's graph the line y equals x. Now we're going from 1 to 3. So our line y equals x won't reach 4. It'll just go up to 3 like that. And then maybe let's do this in green. Here's the square root of x. Like that. All right, so we have y equals x. We have y equals the square root of x. All right, so if we take that same approach that we did last time, where we just take the outside volume, which is formed by rotating the square root of x around the line y equals 4, and then subtract the inside hollowed out part, which is made by taking the line y equals x and rotating around the y equals 4, I think we'll be okay. So the question is what's the radius? Remember, we've talked about drawing these rectangles in. And if I draw the rectangle in for the outer volume, okay, it's this rectangle that gets rotated to create the cylinder. Now, the height of our cylinder is still going to be dx. That's not a big deal. But what is the radius of this cylinder when we rotate it around? What's this distance? Well, remember that this is y equals the square root of x. So from here, from the x-axis up to this point is the square root of x. From the x-axis up to the line y equals 4 is 4. So this radius is 4 minus the square root of x. So the volume for our outer is going to be the integral from 1 to 3 of pi. The radius of our cylinder is 4 minus the square root of x squared dx. All right? So let's find that first. Let's take out our pi. I think it would be easier for us just to FOIL this out and then just take the antiderivative of each part versus you trying to come up with an antiderivative technique here. So when I FOIL this out, I'm going to have a 16. We're going to have minus 8 square roots of x, and then we're going to have a plus x, right? Minus square root of x times minus square root of x is a plus x dx. So this is going to be pi times 16x minus, all right, this would be x to the 3 halves. So we're going to need what? A 16 thirds, I think, in front. When the 3 halves comes down, the 3's will cancel. 16 over 2 is 8 plus x squared from 1 to 3. And just running out of time here, so we'll continue this problem in the next video.